Lesson: Introduction to Julia, High-Performance Programming for AI. Julia has emerged as a prominent programming language in the realm of high-performance computing, particularly in the field of artificial intelligence. Its design philosophy, which emphasizes speed, flexibility, and ease of use, provides a distinct advantage over traditional languages used in AI, such as Python and R. This lesson explores the practical applications of Julia in AI scripting, offering actionable insights into leveraging its unique features to address real-world challenges. By examining tools, frameworks, and step-by-step applications, professionals can enhance their proficiency in using Julia as a high-performance programming tool for AI. Julia's performance is one of its most lauded features, often rivaling that of C and Fortran, which are known for their computational efficiency. This performance advantage is crucial in AI, where large datasets and complex models require substantial computational resources. Julia achieves this speed through its just-in-time compiler, LLVM, which compiles code to machine language just before execution. This approach allows Julia to combine the ease of scripting languages with the performance of low-level languages, providing a significant edge in developing AI applications. One practical example of Julia's application in AI is in the development of neural networks. Julia's Flux.jl is a machine learning library that exemplifies the language's capabilities. Flux is designed to be flexible and easy to use, without sacrificing performance. It integrates seamlessly with Julia's array of computational tools, making it ideal for AI applications that require complex neural network architectures. For instance, building a convolutional neural network in Flux is straightforward, allowing developers to deploy models quickly and efficiently. The concise syntax and high performance of Julia facilitate rapid prototyping and deployment of AI models, as demonstrated in various case studies where Julia outperformed Python in training time for neural networks. Moreover, Julia's ability to handle mathematical computations with ease makes it particularly suitable for implementing algorithms that are computationally intensive. The language's multiple dispatch system enables developers to write highly generic code which can be specialized for different types of data inputs. This feature is beneficial in AI, where algorithms often need to be adapted for various data structures. For example, Julia's differential equations.jl library is widely used for solving complex differential equations in scientific computing, which are prevalent in AI models dealing with dynamic systems. By utilizing Julia's advanced mathematical capabilities, AI practitioners can develop more accurate and efficient models for real-world applications. The ability to interface with other programming languages is another key advantage of Julia, making it a versatile tool in AI scripting. Julia can call C, Fortran, and Python libraries directly, allowing developers to leverage existing libraries and frameworks. This interoperability is particularly useful in AI, where Python's TensorFlow and PyTorch libraries are popular choices for deep learning. Julia's PyCall package enables seamless integration of Python libraries, allowing AI developers to combine Julia's performance with Python's extensive ecosystem. This capability empowers professionals to integrate Julia into their existing workflows without having to completely rewrite their code bases, thus enhancing productivity and reducing development time. In addition to performance and interoperability, Julia's package ecosystem is rapidly growing, offering numerous tools and frameworks tailored for AI development. The Julia community actively contributes to the development of packages such as MLJ.jl, a comprehensive machine learning framework that provides tools for model evaluation, tuning, and composition. MLJ.jl simplifies the process of building and deploying machine learning models by offering a consistent interface for various algorithms and tools. This package is particularly beneficial for AI practitioners who need to experiment with different models and tuning parameters to optimize performance. Furthermore, Julia's support for parallel computing and distributed computing makes it an ideal choice for AI applications that require large-scale data processing. Julia's built-in parallelism capabilities allow developers to easily distribute computations across multiple processors, significantly reducing execution time for data-intensive tasks. This feature is essential in AI, where training and deploying models often involve processing vast amounts of data. By utilizing Julia's parallelism features, AI practitioners can efficiently scale their applications to handle larger datasets and more complex models. Real-world case studies have demonstrated Julia's effectiveness in AI applications. For instance, Julia has been used in the financial industry to develop high-frequency trading algorithms where speed and accuracy are critical. In this context, Julia's ability to perform complex mathematical computations rapidly and accurately has proven invaluable. Similarly, in the field of genomics, Julia has been employed to analyze large-scale genomic data, enabling researchers to identify patterns and insights that were previously difficult to detect with other programming languages. Statistics further underscore Julia's growing adoption in the AI community. A survey conducted by the Julia Computing Organization revealed that over 70% of users reported significant performance improvements in their AI applications after switching to Julia from other languages. This statistic highlights the tangible benefits of using Julia for high-performance AI programming, reinforcing its status as a preferred choice for professionals seeking to enhance their computational capabilities. In conclusion, Julia offers a compelling solution for high-performance programming in AI. Its unique combination of speed, flexibility, and ease of use makes it an ideal choice for developing and deploying AI applications. By leveraging tools and frameworks such as Flux.jl, MLJ.jl, and differential-equations.jl, professionals can harness Julia's capabilities to address real-world challenges and improve their proficiency in AI scripting. Moreover, Julia's interoperability with other languages and support for parallel computing further enhance its utility in complex AI workflows. As the demand for high-performance AI solutions continues to grow, Julia stands out as a powerful and versatile tool that empowers professionals to develop efficient and effective AI applications.